Hello and welcome to Space Mysteries. In tonight's video, we will explore the birth and death of stars. Before we start, press the subscribe button and turn on notifications to never miss a video of the never-ending space and its mysteries. In the beginning, there is only darkness. Not the darkness of a room at night, but something far deeper, far older. This is the darkness of space itself, cold and patient, stretching across distances that swallow human comprehension whole. And yet, even in this vast emptiness, something stirs, something waits. The universe is not truly empty, you see. It never has been. Between the stars, in the regions we might mistake for nothing at all, there are clouds. Molecular clouds, astronomers call them, though that clinical name barely captures their majesty. These are clouds of hydrogen and helium mostly, the simplest elements, the building blocks left over from the universe's own birth some 13.8 billion years ago. They drift through the void, these clouds, some of them so large they could swallow 1,000 solar systems and still have room to spare. They are cold, these places, cold beyond cold, just a few degrees above absolute zero, that temperature where even atoms barely move, where motion itself seems to surrender to the infinite patience of space. And in this cold, in this darkness, in this seeming emptiness, stars are born. Not quickly, never quickly. The universe does not rush. It has time, all the time there ever was or will be, and it uses that time lavishly, extravagantly, as if time costs nothing at all. Inside these molecular clouds, over millions of years, something begins to happen. Gravity, that gentlest and yet most inexorable of forces, begins its ancient work. A cloud might remain undisturbed for eons, drifting in perfect stillness, and then something disturbs it. Perhaps a nearby star explodes, sending a shockwave rippling through space like a stone dropped in still water. Perhaps two galaxies brush against each other in their slow cosmic dance, and the gravitational turbulence reaches across the light years to nudge a cloud just so. Or perhaps the cloud simply grows dense enough, heavy enough, that its own gravity begins to pull it inward, collapsing toward its center like a whispered secret, folding in on itself. The collapse begins slowly, almost imperceptibly. The cloud contracts. As it contracts, it begins to spin, slowly at first, then faster, the way a figure skater spins faster when they pull their arms in close. And as it spins, it flattens, forming a disk of gas and dust spiraling around a growing center. At the heart of this disk, material accumulates. More and more gas falls inward, drawn by gravity's patient pull. The center grows denser, and as it grows denser, it grows warmer. This is one of the universe's most beautiful ironies, that in the coldest reaches of space, heat is being born. The falling gas compresses, and compression creates heat, just as pumping air into a bicycle tire makes the pump grow warm in your hands. But this is compression on a scale beyond imagining. Millions upon millions of tons of gas falling inward, pressing together, heating. At first, the heat is modest, barely a whisper of warmth in the cosmic cold. But the collapse continues, year after year, century after century, millennium after millennium. The center grows hotter, thousands of degrees, tens of thousands of degrees. The gas at the core is no longer simply gas, it has become plasma, a state of matter where electrons are stripped from atoms, where matter exists in a furious dance of charged particles. And still the temperature rises, still gravity pulls more material inward. This object, this growing sphere of hot gas at the center of a swirling disk, is not yet a star. Astronomers call it a protostar, a star in the process of becoming. It glows now, this protostar, glows with the heat of its own compression. If you could see it through the thick cocoon of dust and gas that surrounds it, you would see something magnificent, a reddish sphere, perhaps several times larger than the sun will eventually become, pulsing with infrared light, warm but not yet truly hot, shining but not yet burning. For hundreds of thousands of years, the protostar continues to grow and continues to heat. The disk around it feeds it, spiraling material inward in a slow gravitational cascade. But something is approaching, something inevitable, something that will change everything. At the core of the protostar, where the pressure is greatest, where the temperature has climbed to millions of degrees, the very fabric of matter begins to transform. Hydrogen nuclei, protons, normally repel each other. They are both positively charged, and like charges push each other away. But at these temperatures, at these pressures, the protons are moving so fast, colliding with such energy, that they overcome their mutual repulsion. They smash together, these protons, and when they do, something miraculous happens. They fuse. They combine to form helium, a heavier element. And in that fusion, in that joining, a tiny amount of mass disappears. Where does it go? It becomes energy, pure energy. Released according to Einstein's famous equation, that elegant little formula that says energy equals mass times the speed of light squared. The speed of light is a very large number. When you square it, it becomes unimaginably large, so even a tiny amount of mass, when converted to energy, releases power beyond comprehension. And suddenly, in the core of this protostar, energy blazes forth. Not chemical energy like the fire of burning wood, not gravitational energy like the heat of compression. This is nuclear energy, the energy that holds atomic nuclei together, now released in a torrent of light and heat. The protostar has ignited. It has become a star. For the first time in its existence, it is truly shining, truly burning, though burning is perhaps the wrong word. This is not combustion, this is transmutation. This is the very essence of matter being rearranged at the most fundamental level. This is fusion, and it will continue, if the star is like our sun, for 10 billion years. 10 billion years. Let that number rest in your mind for a moment. 10,000 million years. Every second of every minute of every hour of every day of every year, for 10 billion years, the star will burn. It will fuse hydrogen into helium in its core, releasing floods of energy that push outward against the gravity trying to crush the star inward. And in this balance, this perfect equilibrium between the inward pull of gravity and the outward push of radiation pressure, the star becomes stable. It settles into what astronomers call the main sequence, that long, steady phase of stellar life where most stars spend most of their existence. Our Sun is there now, in the middle of its main sequence life, about 4.6 billion years into that 10 billion year journey. But not all stars are born equal. Some stars are small, dim, red dwarfs that might be only a tenth the mass of our Sun. These miserly stars burn their fuel so slowly, so carefully, that they might live for trillions of years, far longer than the current age of the universe. They will still be shining long after stars like our Sun have died and gone cold. Other stars are monsters, blue giants and supergiants with 50 or 100 times the mass of the Sun. These stars burn bright and hot, pouring out energy at a profligate rate, living fast and dying young. A star 100 times the mass of the Sun might live only a few million years, a cosmic eye blink, burning through its fuel supply in a blaze of glory before meeting a spectacular end. The life of a star is, in many ways, a struggle against its own gravity. Gravity is always pulling inward, always trying to collapse the star into the smallest, densest form possible. But while fusion burns in the core, the energy released pushes outward, holding the star up against gravity's crush. It is a delicate balance, this equilibrium, and it depends entirely on the star having fuel to burn. For most of a star's life, that fuel is hydrogen, the most abundant element in the universe, the simplest atom, a single proton orbited by a single electron. In the core of the star, the hydrogen fuses into helium, 4 hydrogen nuclei combining through a series of reactions to form one helium nucleus. And that helium accumulates in the core, gradually building up, ashes from the fusion fire that powers the star. For billions of years, if the star's like our Sun, this continues unchanged. The star sits on the main sequence, steady, stable, converting hydrogen to helium at a rate that keeps it puffed up against gravity's inward pull. But eventually, inevitably, the hydrogen in the core runs low. Not all the hydrogen in the star, mind you. Most of the star is still hydrogen, but the core, where the temperature and pressure are high enough for fusion, eventually depletes its hydrogen supply. And when that happens, when the fuel runs out, the balance shifts. The outward pressure from fusion decreases. Gravity, patient gravity, begins to win. The core contracts, compressing, heating as it compresses. And as the core heats, something interesting happens in the layers just outside the core. There, in a shell around the now helium core, hydrogen is still present. And now, with the core hotter, the temperature in this shell climbs high enough for fusion to ignite there. The star now burns hydrogen in a shell around its core rather than in the core itself, and this changes everything. The energy released from this shell fusion is greater than what the core was producing before. The star begins to swell, its outer layers expand, growing larger, cooler, redder. The star is becoming a red giant. If the star is like our Sun, it will grow to perhaps 100 times its current diameter, swelling until it engulfs the inner planets of its solar system. Mercury certainly will be consumed, Venus likely. Even Earth might be swallowed, or at least scorched to a lifeless cinder as the Sun's surface draws near. But this is still billions of years in our future, and the Sun burns peacefully on, a middle-aged star with eons of life ahead before these changes come. As the red giant swells, its core continues to contract. The helium ashes at the center, the products of all those billions of years of hydrogen fusion, pack tighter and tighter together. The temperature climbs 10 million degrees, 20 million, 50 million, 100 million degrees, and at these temperatures, even helium nuclei, which repel each other more strongly than hydrogen nuclei do, begin to fuse. Helium fusion is a delicate process, requiring 3 helium nuclei to come together almost simultaneously to form carbon. It is called the triple alpha process, because helium nuclei are also called alpha particles, and 3 of them combine. This fusion of helium into carbon releases energy, not as much as hydrogen fusion, but enough to once again stabilize the star, to hold it up against gravity's crush. For stars like the Sun, this helium-burning phase lasts perhaps 100 million years, a brief coda to the billions of years spent fusing hydrogen. The star settles into a new equilibrium, burning helium in its core, hydrogen in a shell around the core. But the helium too will run out, just as the hydrogen did. And when it does, the core will contract again, growing hotter still. And in stars massive enough, carbon begins to fuse, creating oxygen, neon, magnesium. Each successive fusion process releases less energy than the one before, requires higher temperatures, and lasts for a shorter time. The star is approaching the end of its life, and how that end comes depends crucially on the star's mass. For stars like our Sun, stars of modest mass, the end comes relatively gently. When the helium in the core is exhausted, the core contracts one more time, but it is not massive enough to heat to the temperatures required for carbon fusion. Instead, the core becomes something strange and wonderful, a white dwarf. The outer layers of the star, no longer held up by fusion energy, drift away into space, forming a beautiful structure called a planetary nebula. These are some of the most lovely objects in the universe, glowing shells of gas lit from within by the ultraviolet light of the white dwarf at their center. They come in astonishing variety: rings, spheres, hourglasses, butterflies of light expanding slowly through space. They shine for a few tens of thousands of years and then fade, dispersing their material back into the interstellar medium, back into the great clouds from which new stars will eventually form. And at the center sits the white dwarf, the remnant core of the star, a sphere perhaps the size of Earth, but containing as much mass as the Sun. This is matter compressed to extraordinary densities. A teaspoon of white dwarf material would weigh as much as an elephant. The atoms in a white dwarf are crushed so tightly together that the structure of matter itself begins to break down. Electrons, normally confined to orbits around atomic nuclei, are squeezed out, forming a sea of electrons that permeates the white dwarf. This sea of electrons provides a pressure, called electron degeneracy pressure, that holds the white dwarf up against gravity. No fusion burns in a white dwarf. It shines only with leftover heat, cooling slowly over trillions of years, fading from white to yellow to red to brown, eventually becoming a black dwarf, a cold, dark cinder drifting through space. Though the universe is not yet old enough for any black dwarfs to exist, even the oldest white dwarfs are still faintly glowing. But for more massive stars, stars more than about 8 times the mass of the Sun, the ending is very different indeed. These stars have enough mass that their cores can continue fusing heavier and heavier elements. Carbon fuses to oxygen and neon. Neon fuses magnesium and silicon. Silicon fuses to iron. The star becomes like an onion, with layers of different elements fusing in concentric shells around the core. And each fusion process happens faster than the one before. Hydrogen fusion lasts billions of years, helium fusion hundreds of millions, carbon fusion thousands of years, silicon fusion just days. The star is racing now, racing toward an ending as spectacular as any event in the universe. Iron is the end of the road. Iron nuclei are the most stable nuclei in the universe, the most tightly bound. Fusing iron does not release energy, it consumes energy. And so when the core of a massive star turns to iron, fusion stops. The iron core grows as the silicon shell around it continues to fuse, adding more iron to the core with each passing second. The core grows, and as it grows, gravity compresses it. Electron degeneracy pressure holds it up for a time, the same pressure that supports a white dwarf. But the iron core is far more massive than a white dwarf would be, and it is still growing, still adding mass. And there is a limit, a threshold, about 1.4 times the mass of the Sun, beyond which electron degeneracy pressure cannot hold. It is called the Chandrasekhar limit, named for the physicist who calculated it. When the iron core exceeds this limit, disaster strikes. The core collapses, not slowly, not gradually. In less than a second, the core implodes, falling inward at speeds approaching a quarter of the speed of light. Electrons are crushed into protons, forming neutrons. Matter is compressed to densities beyond imagining, nuclear densities, where the entire mass of the star's core is packed into a sphere perhaps 20 kilometers across. And then, suddenly, the collapse stops. The neutrons themselves provide a new kind of pressure, neutron degeneracy pressure, far stronger than electron degeneracy pressure. The collapse halts, and the infalling material rebounds, bouncing off the incredibly dense neutron core. A shock wave forms, racing outward through the star at thousands of kilometers per second. The star explodes. This is a supernova, one of the most energetic single events in the universe. For a few weeks, a single supernova can shine as brightly as an entire galaxy, outshining billions of normal stars. The explosion releases as much energy in a few seconds as the Sun will release in its entire 10 billion-year lifetime. And in that explosion, in those few seconds of unimaginable violence, the heavy elements are forged. Gold and silver, platinum and uranium. All the elements heavier than iron are created in the inferno of the supernova, in the intense heat and pressure of the explosion. These elements, along with all the lighter elements forged in the star's core over its lifetime, are blasted out into space at tremendous speeds. The star, which took millions of years to form and millions of years to live, is destroyed in an instant, torn apart, scattered across light years of space. And yet, even in this destruction, there is creation. The material ejected by the supernova, enriched with heavy elements, mixes with the interstellar clouds. It seeds them with the raw materials for planets, for rocks, for life. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood was forged in the heart of a star and then scattered into space by a supernova billions of years ago. You are made of stardust, quite literally. The universe has created you from the ashes of dead stars. And when you die, when the Earth dies, when the Sun dies, those atoms will return to space, to be incorporated someday into new stars, new planets, perhaps new forms of life. The universe recycles its matter over and over in a cosmic cycle of birth and death and rebirth that has continued for billions of years and will continue for billions more. At the heart of the supernova, the neutron core remains. This is a neutron star, one of the strangest objects in the universe. A neutron star packs more mass than the Sun into a sphere the size of a city. A teaspoon of neutron star material would weigh as much as a mountain. The surface gravity is so intense that if you could somehow stand on a neutron star, you would weigh trillions of times more than you do on Earth, and you would be crushed instantly into a layer just atoms thick. Neutron stars spin, often very rapidly, sometimes hundreds of times per second, a legacy of the spinning star that collapsed to form them. And they have magnetic fields, extraordinarily powerful magnetic fields, trillions of times stronger than Earth's. These magnetic fields can channel radiation into beams that sweep around as the neutron star rotates. And if one of those beams happens to point toward Earth, we see a pulse of light each time the star rotates. We call these objects pulsars, and they are among the most precise clocks in the universe, their pulses timed with extraordinary regularity. But for the most massive stars, even a neutron star is not the final fate. For stars more than about 20 times the mass of the Sun, the core that remains after the supernova is too massive for even neutron degeneracy pressure to support. And so the core continues to collapse. It collapses past the neutron star stage, past any form of matter we understand. It collapses to a mathematical point of infinite density, a singularity, surrounded by a region of space where gravity is so strong that not even light can escape. This is a black hole. At the boundary of a black hole, called the event horizon, the escape velocity equals the speed of light. Outside the event horizon, light can still escape, though with difficulty. Inside the event horizon, nothing can escape. Anything that crosses the event horizon is lost forever, pulled inexorably toward the central singularity. Black holes are perhaps the most mysterious objects in the universe. They are invisible, at least directly, because they emit no light. We detect them only by their gravitational effects, by the way they bend light around them, by the material that falls into them, heating to millions of degrees and shining brightly just before it crosses the event horizon and disappears. At the centers of most large galaxies, including our own Milky Way, there are supermassive black holes containing millions or billions times the mass of the Sun, their origins still not entirely understood. These cosmic engines power some of the brightest objects in the universe, quasars, as matter swirls into them in vast accretion disks. But the stellar mass black holes, formed from the deaths of massive stars, are far more common, scattered throughout the galaxy, dark, silent guardians of dead stars' memories. And so the cycle continues. Stars are born from clouds of gas and dust. They live, fusing hydrogen into helium, helium into carbon, carbon into iron. They die, gently for small stars, catastrophically for large ones. They return their material to space, enriched with the products of fusion. That material forms new clouds, which collapse to form new stars. Some of those stars have planets. On some of those planets, chemistry becomes complex enough to support life. And at least one of those planets, life evolves intelligence, evolves consciousness, evolves beings that can look up at the night sky and wonder about the stars, wonder where they came from, wonder what they are, wonder at their own existence. The universe has become aware of itself through us. We are the universe contemplating itself, stardust pondering stardust. The night sky, that vast darkness scattered with points of light, is not what it seems. Each of those points is a sun burning with nuclear fire. Some are younger than our sun, still in their vigorous youth. Some are older, swelling into red giants, approaching their ends. Some of the stars you see are already dead, their light still traveling toward us across the years, across the centuries, across the millennia. Light travels fast, but the distances between stars are so vast that light itself takes years to cross them. When you look at the stars, you are looking into the past. The nearest star, Proxima Centauri, is about 4 light-years away. When you see it as it was 4 years ago. Other stars are tens, hundreds, thousands of light-years distant. You see them as they were when Rome was falling, when the pyramids were being built, when humanity was first learning to use fire. There are stars in the night sky that died while the light now reaching your eyes was in transit, their light still traveling across the void long after the star itself exploded or faded. And there are stars being born right now, this very moment, in distant molecular clouds, protostars igniting, beginning the long, slow burn that might last billions of years. The universe is not static, it is dynamic, alive in its own way, constantly changing, stars being born and dying, galaxies colliding and merging, the whole vast cosmic dance continuing on scales of space and time that dwarf human experience. And yet, for all its grandeur, the universe is governed by simple rules, elegant laws that we have, through patience and careful observation, managed to decipher. Gravity pulls massive objects together. Pressure pushes things apart. Energy and mass are interchangeable. Fusion releases energy by combining light elements into heavier ones. These simple principles playing out over billions of years across billions of light years give rise to the rich complexity we see, the stars and galaxies, the planets and moons, the chemistry and biology, the consciousness and culture. The universe is a place of astonishing creativity, building complexity from simplicity through the patient application of natural law. Stars are, in a sense, machines. Machines for turning simple elements into complex ones, for creating the raw materials from which planets and life can form. But they are also, in their way, alive. They are born, they live, they change, they age, they die. They interact with each other gravitationally, sometimes violently when two stars orbit closely and matter streams from one to the other. They have life cycles as varied as any biological organisms. Some live fast and die young. Some live slowly and carefully, eking out their fuel supply over trillions of years. Some die gently, fading away quietly. Some die in spectacular explosions that briefly outshine galaxies. And from their deaths, new stars are born, carrying forward the legacy of matter processed through stellar furnaces, enriched and complexified, generation after generation of stars. Our Sun is a third-generation star, at least. The material from which it formed had already been through at least 2 previous cycles of stellar birth and death. The hydrogen and helium are primordial, left over from the Big Bang itself. But the heavier elements, the carbon and oxygen and iron and all the rest, were forged in stars that lived and died before the Sun was born. Stars whose very light has long since faded, whose names we will never know, whose stories are lost to time. And yet their legacy surrounds us. The earth beneath your feet, the air in your lungs, the water you drink, the food you eat, all of it is made from the ashes of dead stars. You are intimately connected to the cosmos, not metaphorically, but literally, physically, atomically. The universe is not something out there, separate from you. You are part of it, woven into its fabric, a pattern of matter and energy that arose from stellar processes billions of years ago, and will return to those processes when you and the Earth and the Sun eventually end. There is a comfort in this, perhaps, a sense of connection, of belonging. You are not separate from nature, not apart from the universe. You are deeply, fundamentally part of it. Your atoms have been part of many things before they were part of you. Before they were in your body, they might have been in the air, in the ocean, in a tree, in an animal, in the earth, in a comet, in a protoplanetary disk, in a molecular cloud, in a dying star. And after they are no longer part of you, they will become part of other things. Nothing is truly lost in the universe. Matter and energy transform, but they continue. The universe is a place of constant change, but also of deep continuity. On a clear night, far from city lights, you can see the Milky Way, that band of light arcing across the sky. That is our galaxy, seen from within, the combined light of billions of stars too distant and numerous to see individually. The galaxy is vast, some 100,000 light-years across, containing perhaps 400 billion stars. Our Sun is just one of those stars, unremarkable in most respects, orbiting the galactic center at a distance of about 26,000 light-years, taking some 230 million years to complete one orbit. The Sun has been around the galaxy about 20 times since it formed. It will go around perhaps 20 more times before it dies. The galaxy itself was here long before the Sun and will be here long after. It is estimated to be about 13 billion years old, almost as old as the universe itself, formed from the gravitational collapse of a vast cloud of primordial gas in the early universe. And the Milky Way is just one galaxy among billions. In every direction, as far as the most powerful telescopes can see, there are galaxies. Spirals like the Milky Way, ellipticals, irregulars, galaxies of every shape and size. The universe contains at least 2 trillion galaxies, perhaps many more. And each galaxy contains billions or trillions of stars. The total number of stars in the observable universe is estimated at around 10 to the 24th power, 1 followed by 24 zeros, a trillion trillion. And around many of those stars are planets, and on some fraction of those planets, conditions are right for life. And on some fraction of those life-bearing planets, life might evolve intelligence. The universe is likely teeming with life, though the distances between stars are so vast that we may never encounter other intelligent species. We are, perhaps, like isolated islands in a vast ocean, knowing that other islands exist, but unable to reach them. The stars that fill the night sky, the stars that live and die across billions of years, are part of a much larger story, the story of the universe itself. The universe began, as far as we can tell, about 13.8 billion years ago in an event we call the Big Bang. The universe erupted from a state of unimaginable density and temperature, expanding, cooling, matter forming from energy, protons and neutrons forming from quarks, atoms forming from protons and neutrons. For the first few 100,000 years, the universe was opaque, filled with hot plasma that scattered light. But then it cooled enough for electrons to combine with nuclei, forming neutral atoms, and the universe became transparent. Light could travel freely, and that light, redshifted by the expansion of the universe, still reaches us today as the cosmic microwave background, a faint glow visible in every direction, the echo of the Big Bang itself. After the universe became transparent, there was a period known as the Dark Ages, a time before the first stars formed. The universe was filled with hydrogen and helium gas, cooling, slowly collapsing under its own gravity into denser and denser clouds, and then, perhaps 100 million years after the Big Bang, the first stars ignited. These first stars were different from stars today. The universe contained only hydrogen and helium, no heavier elements yet, and stars made purely of hydrogen and helium behave differently. They tend to be very massive, very hot, very bright, and very short-lived. These first stars lit up the universe, ending the Dark Ages, their ultraviolet light ionizing the surrounding hydrogen, creating bubbles of ionized gas that gradually merged until the entire universe was re-ionized. And these first stars died quickly, living only a few million years before exploding as supernovae, seeding the universe with the first heavy elements, making possible the formation of later generations of stars, smaller stars, stars like the Sun, stars that could form rocky planets, stars that could host life. The universe has been evolving ever since, galaxies forming and growing, stars being born and dying, heavy elements accumulating generation by generation, the universe becoming richer, more complex, more interesting. And this process will continue for a very long time. The universe is still young in a sense. Star formation will continue for trillions of years, as long as there is hydrogen gas to form new stars. But eventually, the gas will be used up, locked into stars and brown dwarfs and planets and stellar remnants. New stars will become rarer and rarer. The universe will grow darker. The long-lived red dwarfs will continue to burn for trillions of years, but eventually even they will exhaust their fuel and fade. The white dwarfs will cool, becoming black dwarfs. The neutron stars and black holes will remain, dark and cold and inert. The universe will enter what cosmologists call the degenerate era, an age where no fusion burns anywhere, where the only light comes from the occasional collision of brown dwarfs or the faint glow of proton decay, if protons do indeed decay. And beyond that, unimaginably far in the future, even the black holes will evaporate through a quantum process called Hawking radiation. The universe will be filled with nothing but low-energy photons and perhaps some elementary particles, spread thin and growing thinner as the universe continues to expand. This is the heat death of the universe, a state of maximum entropy, where no complexity can exist, where no change can occur, where time itself, in a sense, loses meaning because nothing happens to mark its passage. This is the ultimate fate of the universe, as far as we can tell, though our understanding of physics at these extreme scales is still incomplete, and it is possible that something we do not yet understand could change this prediction. But that end is so far in the future as to be almost meaningless. The universe today is vibrant, alive with stars and galaxies, rich with complexity and possibility. We live in what might be called the stelliferous era, the age of stars, when the universe is bright and interesting, when stars are being born and dying, when planets form and life emerges, when intelligence arises and contemplates the cosmos. This era will last for trillions of years, a vast span of time compared to the few billion years that have passed so far. We are, in cosmic terms, near the beginning of the story, not the end. The stars will continue to shine. New stars are being born even as others die. In the Eagle Nebula, in the pillars of creation, dense columns of gas and dust are collapsing, forming stars right now. In the Orion Nebula, young stars have recently ignited, their light illuminating the cloud from which they formed. In the Carina Nebula, massive stars are living fast and bright, destined to explode as supernovae in the near cosmic future. All across the galaxy, all across the universe, stars are being born, living, dying, the great cycle continuing, the universe constantly renewing itself. And we are here to witness it. We are here, briefly, for a few decades out of the billions of years of cosmic history, but we are here and we can look up and see the stars and understand, at least in part, what they are and how they work. We can trace the life cycles of stars from their birth in molecular clouds to their death as white dwarfs or neutron stars or black holes. We can understand that the atoms in our bodies were forged in stellar furnaces. We can grasp, if only intellectually, the vast scales of space and time on which the universe operates. This is a profound achievement, this understanding. For most of human history, the stars were mysteries, lights in the sky whose nature was unknown. Only in the last few centuries have we begun to understand them, to see them not as mysterious lights, but as distant suns, subject to the same physical laws that govern the earth. And with that understanding comes a kind of humility, a recognition of our place in the cosmos. We are small, so very small, inhabitants of a tiny planet orbiting an unremarkable star in the outer regions of an ordinary galaxy among trillions of galaxies. Our lives are brief, our civilization younger than many stars, our entire species a newcomer on cosmic timescales. And yet, for all our smallness, we are part of something grand, something beautiful, something meaningful. We are the universe becoming conscious, matter organized in such a way as to contemplate itself. We are rare, perhaps, maybe even unique in our particular form, but we are also deeply connected to everything else, woven into the fabric of the cosmos. There is something deeply peaceful in contemplating the stars, in thinking about the slow, patient processes that create them and destroy them. The universe operates on timescales so vast that human concerns, human conflicts, human anxieties fade into insignificance. The star does not hurry. The galaxy does not rush. They have time, all the time there is. They unfold according to natural law, patiently, inexorably, creating beauty and complexity through the simple operation of physical principles. And we, for all our brief span, can appreciate that beauty, can understand those principles, can find meaning and wonder in the contemplation of the cosmos. The night sky is always there, waiting. The stars are always shining, even when we cannot see them, hidden by daylight or clouds or the lights of the city. They are ancient, most of them far older than human civilization, older than the human species, older than complex life on Earth. And they will continue long after we are gone, shining steadily, burning through their fuel, following the trajectories laid down by the laws of physics. There is a continuity in the stars, a sense of the eternal, even though each individual star is born and dies. The cycle continues, stars forming from the ashes of earlier stars, generation after generation, an unbroken chain stretching back to the first stars and forward into the unimaginable future. You are part of this story, not separate from it, not observing it from outside, but woven into it, implicated in it at the most fundamental level. The atoms in your body are not your atoms. They do not belong to you. They are simply on loan, part of you for a brief time before returning to the world, to the cycle, to the cosmos. You are a temporary pattern, a wave passing through the ocean of atoms, a brief moment of organization in the endless flux of matter and energy that is the universe. And yet, while you exist, while the pattern holds, you are something remarkable. You are consciousness arising from chemistry, awareness emerging from the arrangement of atoms, meaning created from matter. You are the universe looking at itself with wonder. The stars that gave birth to your atoms died long ago, billions of years before you were born, perhaps before the Earth itself existed. They lived their lives, burned their fuel, and died, and in dying scattered the materials that would eventually become you across the void. Those atoms drifted through space, perhaps for millions of years, cold and dark and separate. They joined molecular clouds, were swept up in the collapse that formed the solar nebula, the disk of gas and dust from which the sun and planets formed. Some became part of the Earth, buried in rock, dissolved in the ocean, drifting in the atmosphere. They cycled through the biosphere, through countless organisms, through the food chain, through rain and rivers and soil and air. And eventually, they came together in you, organized into the intricate structure of a human body, a human brain, a human mind. And someday, not too far in the future on cosmic scales, those atoms will leave you. They will return to the Earth, and from there continue their journey. Perhaps they will become part of other living things. Perhaps they will be buried deep in sediment, to be uplifted millions of years hence as mountains rise. Perhaps they will be subducted into the mantle, melted, recycled through the slow churn of plate tectonics. And in about 5 billion years, when the sun begins to die, when it swells into a red giant and engulfs the Earth, or at least scours it clean of all life, those atoms will be liberated again, cast back into space, to drift once more through the galaxy, to perhaps someday become part of new stars, new planets, new forms of life we cannot imagine. The journey continues, the cycle turns. The universe endlessly rearranges itself into new patterns, new configurations, exploring the space of possibilities. The death of stars is not an ending, but a transformation. The matter and energy are not destroyed, merely changed, redistributed, made available for new creations. The supernova that destroys a star also seeds space with heavy elements, making possible the chemistry of life. The white dwarf that remains when a sun-like star dies will cool for trillions of years, but the planetary nebula it creates enriches the interstellar medium. Even black holes, those ultimate destroyers, those points of no return, may not be permanent. Stephen Hawking showed that black holes should very slowly evaporate through quantum effects, releasing their mass energy back into the universe over timescales so vast they are barely conceivable, timescales measured in Google years, 10 to the 100th power years, far longer than the current age of the universe. Nothing is permanent. Everything changes. The universe is a vast engine of transformation, endlessly creative, endlessly inventive. Consider for a moment the sheer improbability of your existence. The atoms in your body had to be in exactly the right place at exactly the right time. The Earth had to form at exactly the right distance from the Sun, in exactly the right orbit, with exactly the right composition. Life had to arise, had to survive billions of years of catastrophe and change, had to evolve from simple cells to complex multicellular organisms, to plants and animals, to vertebrates, to mammals, to primates, to humans. Your ancestors had to survive, every single one of them, going back not just to the first humans, but to the first mammals, the first vertebrates, the first animals, the first life. Every single one of your ancestors, going back 4 billion years, had to survive long enough to reproduce. If any one of them had died before having children, you would not exist. The chain would be broken. The probability is infinitesimally small, and yet here you are, impossible and yet inevitable, a product of countless chance events, and yet also the predictable outcome of natural law operating over vast spans of time. And the same is true of the stars. Each star is unique, formed from a particular cloud at a particular time, under particular conditions. The details matter. A cloud that is a little denser will collapse a little faster and form a larger star. A cloud with a little more angular momentum will form a more rapidly rotating star. A cloud seeded with material from a nearby supernova will have more heavy elements and will form a different kind of planetary system. Every star is shaped by its history, by the events that led to its formation, by the environment in which it exists. And yet, for all their uniqueness, all their individuality, stars follow predictable patterns. Stars of a given mass will evolve in similar ways, will have similar lifetimes, and will die in similar fashions. The details differ, but the broad outlines are determined by physics, by the inexorable logic of gravity and pressure, fusion and radiation. There is something profound in this combination of predictability and uniqueness, of law and chance, of necessity and contingency. The universe is governed by laws, but the application of those laws leads to vast diversity, to endless variety. No two stars are exactly alike, no two planets are identical, no two galaxies have the same structure. And yet, all stars burn through fusion. All planets are held in orbit by gravity. All galaxies are shaped by dark matter and rotation. The universe is both orderly and chaotic, both lawful and random, both predictable and surprising. This is part of its beauty, this tension between order and disorder, between pattern and randomness. In recent decades, astronomers have discovered thousands of planets orbiting other stars, exoplanets, worlds beyond our solar system. These planets are astonishingly diverse. Hot Jupiters that orbit their stars in just days, their surfaces scorched to thousands of degrees. Super-Earths, planets larger than Earth but smaller than Neptune, a type of planet that does not exist in our solar system. mini-Neptunes, ice giants, lava worlds, water worlds, planets that orbit binary stars, planets that orbit pulsars, planets that drift freely through space unattached to any star. The galaxy is rich with worlds, far more diverse than we imagined even a generation ago. And around every star there is the possibility of planets, and on some fraction of those planets, conditions suitable for life. The universe is not just stars and galaxies, empty space and radiation. It is also worlds, surfaces, atmospheres, oceans perhaps, life perhaps, intelligence perhaps. We are beginning to understand that we are not alone in the universe, not in the sense of intelligent aliens necessarily, though they may exist, but in the sense that the processes that led to the Earth and to life are not unique, not singular, but common, happening around countless stars across the cosmos. The stars, then, are not just balls of burning gas, not just fusion reactors converting hydrogen to helium. They are the parents of planets, the creators of worlds, the forges in which the materials of life are made. They are the engines of cosmic evolution, driving the universe from simplicity to complexity, from a featureless soup of hydrogen and helium to a rich tapestry of elements and molecules, structures and systems. Without stars, the universe would be a cold, dark, lifeless place, filled with primordial gas slowly cooling toward absolute zero. With stars, the universe comes alive, becomes dynamic, becomes interesting. Stars create light and heat, they create heavy elements, they create the conditions for planets and chemistry and life and consciousness. They are, in a very real sense, the reason anything interesting exists at all. And yet, stars are fragile in their way. They exist in a precarious balance between gravity pulling inward and pressure pushing outward, between matter and energy, between mass and light. Disturb that balance and the star changes, evolves, dies. The equilibrium is maintained by fusion, and fusion requires fuel, and fuel is finite. Every star, no matter how massive, no matter how bright, is burning through a limited supply of hydrogen, helium, heavier elements. Every star is mortal. Every star will die. This is not a tragedy, but simply a fact, a consequence of the laws of physics, a necessary part of the cosmic cycle. Death makes room for new life, for new stars, for new possibilities. If stars lived forever, if they burned eternally without consuming their fuel, the universe would quickly fill with old stars. All the gas would be locked up in stellar bodies. No new stars could form. Stellar death is necessary for stellar birth. The cycle requires both. There is a particular kind of binary star system that illustrates this beautifully. Systems where a white dwarf orbits close to a normal star, close enough that the white dwarf's gravity pulls material from the companion star's outer layers. This material spirals down onto the white dwarf, forming an accretion disk, heating as it falls. The white dwarf grows more massive as it accretes material from its companion. And if it accretes enough mass, if it approaches that critical limit of 1.4 solar masses, something remarkable happens. The pressure and temperature at the center of the white dwarf become high enough for carbon fusion to begin. But unlike in a normal star, where pressure would rise and the star would expand and cool, stabilizing the fusion, in a white dwarf the matter is degenerate. Degenerate matter does not expand when heated. The fusion begins, the temperature rises, the fusion rate increases, the temperature rises further, a runaway process. In less than a second, the entire white dwarf undergoes fusion simultaneously. The white dwarf explodes. This is a Type 1a supernova, different from the core collapse supernovae that end the lives of massive stars, but equally spectacular, equally bright. The white dwarf is completely destroyed, torn apart, converted from carbon and oxygen into nickel and iron and other elements, scattered into space at tremendous speeds. These Type 1a supernovae are important to cosmology because they are remarkably consistent in their brightness. They can be used as standard candles, objects of known luminosity, allowing astronomers to measure cosmic distances with great precision. It was observations of distant Type 1a supernovae in the late 1990s that led to the discovery that the expansion of the universe is accelerating, driven by some mysterious dark energy that permeates space. This discovery revolutionized cosmology, showing that the universe is not just expanding, but expanding ever faster, that the galaxies are not just moving apart, but moving apart at an increasing rate. The ultimate fate of the universe depends on this dark energy, this unknown force that seems to make up about 70% of the total energy content of the universe. If dark energy continues to dominate, the universe will expand forever, growing ever colder, ever darker, ever more diffuse, approaching the heat death over trillions upon trillions of years. This is the current best understanding, though much remains uncertain, much remains to be discovered. The stars, in their lives and deaths, have taught us much about the universe. They have revealed the nature of matter and energy, the workings of gravity and nuclear fusion, the history of the cosmos and its ultimate fate. They have shown us that we are made of the same stuff as the stars, that we are connected to the cosmos at the most fundamental level. They have given us a sense of scale, of the vastness of space and time, of the age and size of the universe. They have shown us that the universe is dynamic, changing, evolving, that it has a history and a future, that it is not static or eternal, but was born and will eventually die, though that death is so far in the future as to be almost unimaginable. On a more immediate scale, our own star, the Sun, continues its steady burn at the center of the solar system. It has been shining for about 4.6 billion years, and it will continue to shine, more or less as it does now, for about another 5 billion years. This is a reassuring timescale, far longer than human civilization, longer than complex life has existed on Earth, longer than the Earth has had a solid surface. The Sun is stable, reliable, providing the energy that drives the weather, the ocean currents, the biosphere. Life on Earth is solar-powered, almost entirely. Plants capture sunlight and convert it to chemical energy through photosynthesis. Animals eat plants or eat other animals that eat plants. The energy that powers your body, the energy that lets you think and move and breathe, came ultimately from the Sun, from fusion reactions happening 93 million miles away in the solar core. You are, in a sense, running on starlight, on energy released by the transmutation of hydrogen into helium in the Sun's heart. The Sun loses mass as it shines, converting mass into energy at a rate of about 4 million tons per second. This sounds like a lot, and it is, but the Sun is massive enough that it can sustain this loss for billions of years. Every second, the Sun becomes a little lighter, and that energy radiates out into space in all directions. A tiny fraction of it, less than 1 billionth, strikes the Earth, warming it, illuminating it, making life possible. The rest flows out into the solar system and beyond, eventually escaping into interstellar space, contributing to the faint background of starlight that fills the galaxy. The sun's light will travel for thousands or millions of years, growing ever fainter as it spreads out, before finally becoming indistinguishable from the background radiation of space. But by then, the photons will have journeyed across vast distances, perhaps witnessed the birth of other stars, passed by other planets, carried the sun's message out into the cosmos. There is a meditation practice, common in many traditions, of contemplating vastness, of reflecting on the scale of the universe, the age of the earth, the brevity of human life. This practice is meant to cultivate perspective, to help one see beyond immediate concerns, to recognize the larger context in which one's life unfolds. The stars are perfect objects for such contemplation. They are vast, ancient, and powerful beyond imagination. They operate on timescales that make human history seem like a fleeting moment. They exist in quantities that numb the mind, billions in the galaxy, trillions in the universe, and yet each one is comprehensible, governed by laws we can understand, describable with mathematics and physics. The universe is both overwhelming and intelligible, both incomprehensibly large and surprisingly simple in its underlying principles. Lying under the stars on a clear night, away from artificial lights, one can see the Milky Way stretching across the sky, that river of stars, our home galaxy seen from within. The ancients saw it and imagined it was milk spilled by a goddess, or a road traveled by spirits, or a bridge to the afterlife. Now we know it is stars, billions of them, along with clouds of gas and dust, all bound together by gravity into a vast spiral structure rotating slowly around a supermassive black hole. And yet, for all our scientific understanding, the sight is no less awe-inspiring, no less beautiful. Knowledge does not diminish wonder. If anything, it enhances it, adding layers of meaning and connection to what we see. Each star in that river of light is a sun, potentially with planets, potentially with life. Some of those stars are younger than ours, still in their vigorous youth, burning bright and hot. Some are older, approaching the end of their main sequence lifetimes, beginning the slow evolution toward red giant status. Some are already giants, swollen and red, approaching their ends. Some are white dwarfs, the cooling corpses of dead stars. Some are neutron stars, though their faintness makes them invisible to the naked eye. Some are black holes, dark and silent. The galaxy is filled with stars at every stage of life, a cosmic ecosystem where birth and death are constantly occurring, where matter cycles through stars again and again, enriched and transformed by each passage through a stellar furnace. There are regions of the galaxy, great clouds of gas and dust, where stars are being born right now, this very moment. The Eagle Nebula, the Orion Nebula, the Carina Nebula. These are stellar nurseries, places where gravity is pulling molecular clouds together, forming protostars that will ignite and shine. Infrared telescopes can peer through the dust and see these forming stars, can watch as they gather mass, as they begin to heat, as they approach the critical temperature and density for fusion. In a few 100,000 years, some of these protostars will ignite, will become true stars, will begin the long, steady burn of hydrogen fusion. And perhaps around some of them, planets will form. And perhaps on some of those planets, billions of years hence, life will arise. And perhaps that life will evolve intelligence. and perhaps that intelligence will look up at its own night sky and wonder at the stars, just as we do. The universe is patient. It has time. It is in no hurry. Stars take millions of years to form, billions of years to live, and their deaths, spectacular as they may be, are just brief punctuation marks in the slow cosmic narrative. The scale of time in the universe is difficult for humans to grasp. We live for decades. Our civilizations last for centuries or millennia. But stars live for millions or billions of years. Galaxies persist for tens of billions. The universe itself is nearly 14 billion years old and will continue for trillions more. On these timescales, human concerns, human conflicts, the rise and fall of empires, all of it is ephemeral, vanishingly brief. This is not to say that human life is meaningless, far from it. But it is to recognize that meaning exists in context, that our brief lives unfold against a backdrop of cosmic time, and that the universe will continue long after we are gone, indifferent to our passing, following its own deep rhythms. And yet, there is something profound about consciousness, about awareness, about intelligence. The universe, for most of its history, was presumably unconscious, just matter and energy following natural law, creating structure and complexity, but without any awareness of itself. And then, on at least one planet, around one unremarkable star, matter organized itself in such a way as to become aware, to think, to contemplate, to understand. The universe became conscious of itself through us, and perhaps through other intelligences elsewhere, though we have not yet found them. This seems meaningful, important, even if we are brief and small and localized. We are the universe's way of knowing itself, at least in this corner of space. Through us, the cosmos reflects on its own nature, calculates its own age, maps its own structure, understands its own history and future. This is remarkable. The stars, those great burning spheres of plasma scattered across the sky, are not separate from us. They are our ancestors in a sense. They made us. Without stellar nucleosynthesis, without supernovae, without the death of generations of stars, there would be no heavy elements, no carbon or oxygen or iron, no chemistry complex enough for life. We exist because stars died. Our very existence is predicated on stellar death, on the violent explosions that scattered the products of fusion across the galaxy. We are quite literally children of the stars, descendants of dead suns, heirs to billions of years of cosmic evolution. As you lie in bed, perhaps reading this as you prepare for sleep, you can reflect on this. The atoms in your body, in your brain, in the neurons that are processing these words right now, came from stars. The oxygen you are breathing was forged in stars more massive than the sun. The carbon in your DNA was created through the triple alpha process in red giants. The iron in your blood was synthesized in supernova explosions. You are made of stardust, assembled into a pattern that can think and feel and wonder. And when you sleep, when consciousness fades and dreams take over, the atoms remain, continuing their invisible quantum dance, maintaining the structure that is you until morning comes and you wake and consciousness returns. The night sky is always there, even when you cannot see it, even in daylight when the sun's brightness overwhelms the stars. They are still shining, still burning, still following their long, slow arcs through life toward death. The universe continues, indifferent to whether we observe it, following laws that operated long before humans existed and will continue long after we are gone. And yet, for now, we are here, able to look up and see and understand and wonder. This is a gift, this consciousness, this awareness. It is brief, but it is real. You are real, made of matter that has existed since the beginning, matter that has been part of countless forms before you and will be part of countless forms after you. But right now, arranged as you, aware, thinking, feeling, alive. The stars will continue to burn while you sleep. The galaxy will continue its slow rotation. The universe will continue expanding, carrying the galaxies ever farther apart. New stars will be born, old stars will die. Somewhere, perhaps, in some distant world, another consciousness is also looking up at the stars, also wondering, also trying to understand its place in the cosmos. Or perhaps we are alone, at least for now, the only minds in the universe capable of contemplating the universe itself. Either way, we are here, improbable and yet inevitable, temporary and yet connected to eternity through the atoms that compose us. Rest now, sleep. The universe will continue its slow, patient work, transforming matter and energy, creating and destroying, birthing stars and extinguishing them, following the great cycles that have continued for billions of years and will continue for billions more. You are safe, held by the Earth's gravity, warmed by the sun's light, connected to the cosmos at every level of your being. You are part of the universe, and the universe is part of you. There is nowhere to go, nothing you need to do, nothing you need to be, except what you are. The stars are shining, the universe is unfolding, and you, for this brief moment, are here to witness it, to be part of it, to live within it. Let the vastness of space and time wash over you. Let the billions of years of cosmic history cradle you. Let the knowledge that you are made of stars, that you are stardust contemplating stardust, bring you peace. Close your eyes, breathe slowly, feel the weight of your body, held by the planet, orbiting the sun, moving through the galaxy, traveling through the universe. You are motion within motion, pattern within pattern, consciousness within cosmos. Rest. Dream. The stars will be there when you wake, patient and eternal, burning quietly in the dark, waiting for no one, needing nothing, simply being, simply shining, simply following the path laid down by physics and time. Good night. Sleep well. The universe holds you. The stars watch over you. You are home.